Hi, I'm Tao Xiang from the University of Southern California. In this series of videos, I will present my work on representations of 3D rotations in neural networks. I will prove that in 3D rotation estimation problems, if the output of the neural network is the set of Euler angles or a quaternion, and there is no constraint on the range of possible input rotations, then a maximum error of 180 degrees is inevitable. I will show that, contrary to what one might hope, using an embedding of SO3 does not always solve this problem, as symmetries in the input may cause them to fail. I will explore how an ensemble of networks can be employed to solve this problem. In this presentation, I will only give informal proofs and explanations. For more formal treatment, please refer to the paper. For a long time, Euler angles and quaternions have been the most widely used rotational representations in computer vision and computer graphics. This tradition continues into the deep learning age, but their use in neural networks was not without trouble. It seems that in post-estimation problems, sometimes the output rotation is completely wrong. If the range of possible rotations is small, for example, estimating the pose of a near frontal face, then things generally work fine. But when all rotations are possible, occasional large errors in excess of 100 degrees seem extremely hard to eliminate, despite engineering efforts in improving architecture and training. A plausible guess for the reason is that this is because the mapping from a rotation to these representations is not continuous. To see this more clearly, let's consider the simpler 2D case first. Suppose we have a 2D object that can rotate around its center. One particular position is considered canonical. Given an image of this object, we want to compute its rotation relative to the canonical position with a neural network. Let's say we want the angle to be in the range minus pi exclusive to pi inclusive. If we represent both the input and the output as an angle, then what we want the network to learn is simply an identity function on an interval. Let's call this the reference function. The problem is that the two endpoints of this interval actually represent the same input. Since changing the rotation angle by 2 pi results in the same rotation, we expand the domain to the whole real line. Now it is clear that at all multiples of pi, the reference function is not continuous. On the other hand, the neural network is continuous, so there does not exist a network that computes the reference function correctly everywhere. If we train the network to minimize the difference between the output and the reference, we will get something like this blue function, which gives large errors around pi and minus pi. But this may not be the smartest way to train our network. The conversion from an arbitrary angle to the equivalent angle in the range minus pi to pi is known and simple and can be done as a post-processing step. The output of the network needs not be exactly the same as the reference. They only have to represent the same rotation and can differ by a multiple of 2 pi. If we adopt this view, the loss function should be the difference between the output and the nearest value equivalent to the reference value. And we can see that it no longer corresponds to the distance from the output to the reference function or to any specific function. If we train our network like this, it is possible that we end up getting the green function. Remember that our function must be periodic. It is correct near pi and minus pi, where the reference function is discontinuous, although it gives wrong values at some other places. Similarly, for any specific point, we can always find a continuous function that is correct near that point. Indeed, if we expand the graph to include all equivalent correct values, then the graph would be a union of continuous lines. So we cannot explain why it is impossible to compute the rotation angle correctly everywhere by the discontinuity of a specific reference function. Instead, we must show that any function that computes the rotation angle correctly everywhere must have discontinuities, or equivalently, no continuous function can compute the rotation angle correctly everywhere. It is obvious that any continuous and correct function must follow one of the lines and be strictly monotonic, which is impossible for a periodic function. we can show that for any continuous function that computes the rotation angle, there exists an input rotation such that the output is wrong by an angle of pi, which is the largest possible distance between two 2D rotations. This maximum error will be reached if the input angle and output angle differs by an odd multiple of pi. We mark these points with red lines. These lines divide the plane into disconnected stripes. Take any continuous function f with period 2 pi. Consider the value of f at 0. If f0 lies on a red line, then we're done. Otherwise, it must lie within the stripe. f2 pi equals f0, and it must lie in a different stripe. Since the function is continuous, the graph of the function between 0 and 2 pi must be a continuous curve, so it must intersect with the border between the two stripes, which is a red line. This intersection is where the output of the function is wrong by an angle of pi. To generalize this idea more easily, let's see the same argument in a different form. Here is a two-dimensional object in its canonical position. Underneath, we have marked all correct rotation angles with blue and green triangles, and angles of maximum error with red diamonds. Now let's rotate the object continuously counterclockwise. After a rotation of 2 pi, the object returns to its starting position. But the blue set of correct angles and the green set of correct angles have continuously exchanged their places. Since after a rotation of 2 pi the position is exactly the same, our neural network must give the same output. The pink triangle marks the output of one possible network. If in the starting position the output angle is in the blue region, then after a rotation of 2 pi, it must be in the green region, and vice versa. Since the network is continuous, somewhere between these two states, the output must be on the border between the different colored regions, at which point it gives an error of pi. Let's try adapting this whole thought process to the quaternion representation of 3D rotation. We first examine an argument from discontinuities and try to eliminate the discontinuity to show that such an argument is not sufficient. For each rotation, there are exactly two unit quaternions that represent it, one being the negative of the other. So a conversion from a rotation to a quaternion needs to break ties. Say for a unit quaternion w plus xi plus yj plus zk, we require w to be positive. If it is 0, then we require x to be positive, and so on. We can give this reference conversion function explicitly as a function of rotation matrices. Then the set of valid rotation quaternions will be a 3-hemisphere. A 3-sphere is difficult to visualize. For our purpose, we shall take the two-dimensional section at x equals 0, which is the sphere. We let the w-axis point to the lower left, the z-axis up, the y-axis to the lower right. The range of valid rotation quaternions is marked brown. Now consider the problem of estimating the rotation of a 3D object. The input can be an image, or it can be a point cloud. Again, we start from the canonical position. The correct quaternion is marked with the brown point. Rotate the object counterclockwise around the z-axis. The correct quaternion moves up. Just before the rotation angle reaches pi, the correct quaternion is near the top. But if we rotate the object a little further, to just beyond a half turn, the correct quaternion jumps to the bottom. So our reference conversion function is discontinuous at the half turn around the z-axis. In fact, this is true for a half turn around any axis. Since our network is continuous, if it is trained to minimize the distance between the output quaternion and the reference quaternion, then it will produce a large error here. The distance can be the Euclidean distance or the length of the minor grid arc. It makes no difference. But if we take the alternative view that the output needs not be exactly the same as the reference but only needs to represent the same rotation, then our loss function should be the rotation distance rather than the quaternion distance. A nice property of the quaternion rotation representation is the simple relationship between rotation distance and quaternion distance. If two rotations are represented by quaternions p and q respectively, then the rotation distance measured by an angle is twice the arc length distance from p to the nearest one of q and minus q. So, it is possible to find a continuous function that gives zero error near this discontinuity of the reference function. We mark the value of our function with a pink triangle. When the reference quaternion jumps to the bottom, we can simply continue to move to the right. Now, the pink triangle is the exact opposite of the brown point, but they represent the same rotation, so the rotation distance is zero. We can easily extend this to account for all rotations near this discontinuity. Similarly, for any specific rotation, we can always find a continuous function that is correct around that rotation. So we cannot explain why it is impossible to compute the rotation quaternion correctly everywhere by the discontinuity of a specific reference function. Now, instead of limiting the valid quaternions to one hemisphere, we track all equivalent correct quaternions and see what happens. In the beginning, the object is in the canonical position. Two quaternions representing the rotation are marked with the blue point and a green point. The set of quaternions that have a rotation distance of pi from the correct quaternions are marked red. They form a two-sphere that divides the three-sphere into two disconnected hemispheres, each corresponding to one correct quaternion. As the object starts rotating, the blue quaternion moves up and then to the right. The green quaternion moves down and then to the left. When the object returns to its starting position, the two quaternions have continuously exchanged their places along with the two hemispheres. Since after a rotation of 2 pi, the position is exactly the same, our neural network must give the same output. If in the starting position the output quaternion is in the blue region, then after a rotation of 2 pi, it must be in the green region, and vice versa. Since the network is continuous, somewhere between these two states, the output must be on the border between the different colored regions, at which point it gives an error of pi. Now we have proved that for any continuous function from rotations to unit quaternions, there exists a rotation for which the output represents a rotation that differs from the input by an angle of pi. The case for Euler angles is similar. Depending on the order of rotation axis, there are many different Euler angles. We take the extrinsic x, y, z Euler angle as an example. Since each elemental rotation is a one-parameter 2D rotation, the analysis for Euler angle rotation representation contains the analysis for 2D rotations as a special case. We can rotate the object around the z-axis and track the angle gamma. Alternatively, we can use the fact that there is a continuous function from a set of Euler angles to an equivalent quaternion. Composition of rotations correspond to multiplication of quaternions. So, from a set of Euler angles, we can get a quaternion by multiplying 3 elemental rotation quaternions. Such a mapping is obviously continuous. So, if there exists a continuous function from rotation to Euler angles whose maximum error is smaller than pi, then by composing it with a continuous function from Euler angles to equivalent quaternions, we get a continuous function from rotations to unit quaternions whose maximum error is smaller than pi, which is impossible. So, for any continuous function from rotations to Euler angles, there exists a rotation for which the output represents a rotation that differs from the input by an angle of pi. It seems that the key to the problem is that for certain kinds of representations, the same rotation can be represented differently, and it is possible to move from one representation to another by continuously changing the input. If the range of possible input is limited, then such a thing might not happen. In the next part, we will see what kind of limitation on the input can prevent this. On the other hand, of course, there are rotational representations that does not have this issue, and for which a continuous function from a rotation to its representation does exist. For example, rotation matrices themselves. But in the next part, we will see how symmetries in the input can cause these representations to fail as well.